Hello. In this video, we're going to look at some introductory concepts for vectors. So starting out, a vector is a quantity specified by a magnitude, which is just a fancy way of saying size, and a direction. So for example, if I see something like 4 kilometers west, that is a vector in a way because it is describing something that has a magnitude, a distance, 4 kilometers, along with a direction. So anytime we have something that is directional, things like velocity, which is a speed with a direction, acceleration, displacement, these sorts of things are vectors. We often like to indicate them graphically by having a line with an arrow that's showing a particular direction. A scalar would be magnitude alone. So if I simply say something has a distance of 4 kilometers, that would be a scalar. The scalar equivalent of velocity would be just speed. So just to be clear, this right here, the 4 kilometers west, that's referring to a displacement. And 4 kilometers would just be a distance alone, so just a magnitude. We have several ways of referring to vectors. So I've got 4 different ways of showing a vector right here. One, I can show a vector by 2 points that define the vector, usually the starting point. So in this case, I'm using O to represent the starting point, and A would be another point along the direction of the vector. So vector OA would be from O to A if these are 2 points in coordinate space. We can also name a vector just with a single letter, so V or A or Q or whatever letter we want. When we do a single letter, in typing, we usually make it bold. So this is bold. If I'm writing it by hand, then I put the little vector arrow on top of it to show that it is a vector. We can also define a vector as a position vector using coordinates. Assuming in this case that O is the origin, then the vector OA could be going from the point O, 0, 0, to the point A, where A here is 4, 2. So we can express this as a vector using a vertical matrix, essentially, 4, 2, where the first number refers to the horizontal part of that direction, and the second number refers to the vertical part of the direction, breaking it into its components. Or we can go even further where we have actual component vectors. So I in 2 dimensions refers to the unit vector that is just the horizontal distance. So the horizontal component of any movement, of any vector, would be 1, 0. In other words, 1 unit, whatever that is, in the horizontal direction. J would therefore be the unit vector of the vertical component, 0, 1. So this would be the 4 times the horizontal component, or 4 horizontally, and 2 vertically. We can also use negative, so 2 here would refer to 2 going up, as opposed to negative 2, which would be 2 going down. If I'm working in 3 dimensions, then my component vectors are still, I for the horizontal component, and J for the vertical component. But now because I have a 3rd dimension, I need a 3rd component, and that would be K if I'm working in 3 dimensions. So graphically, what this would look like, what I've drawn here, is I have in my coordinate plane, I said the point A was at 4, 2, O is at the origin, so vector OA refers to this vector between or from O to A. We've got a horizontal component of 4. That's this part. So that's my horizontal component vector. That represents 4I, because I would just be in that direction, but a unit of 1. And this vertical component represents 2J. Now, we would normally want to think of, well, J is along the y-axis, so J is here. This is still 2J. These 2 vectors, 2J, it actually does not matter what their position is because they are direction vectors. They're used to define a direction from whatever our starting point happens to be. So vectors are equal if they have the same direction and magnitude, regardless of whether or not they have the same position. So 2J is 2J no matter how I move it around. So this vector OA would be equivalent maybe to some other vector if I draw a vector here that has the exact same direction and magnitude, I could call that vector v, and vector v does equal OA, even though they're not in the same position. Now, vector addition involves the addition of corresponding components. It is commutative and it is associative. So if, let's say, I have a vector A, and to that I want to add a vector B. Visually, I can think of this as being whatever my vector A is. So let's say this is vector A. To add vector B onto it, I consider the starting position of vector B to be the ending position of vector A. So if vector B goes maybe in that direction for that amount of time or distance, then the summation vector, A plus B, would be the vector that just goes from the start to the finish without having to go to that intermediate point. So visually, that is what vector A plus B should look like. This is commutative because it actually does not matter in what order I add these vectors. So again, if I consider B, if this right here is my starting point, vector B would be a vector in the same direction and with the same length as the one I had already drawn. So what I've drawn in red and what I've drawn in blue for B, those are same length, same direction, and therefore they are equal. And vector A then, starting from that endpoint, I end up in the same place. So A plus B is the same as B plus A. That resultant vector gets me from the same starting point to the same ending point. It does not matter which direction I go first. So that's vector addition. What that means is, let's say vector A was equal to A1, A2, A3. So let's say we have a three-dimensional vector. So those are the three components of A. And vector B, also a three-dimensional vector. If vector B was just a two-dimensional vector, then that just means I have a 0 in the third dimension. So B1, B2, B3. And so then the sum of them, A plus B or B plus A, because it is commutative. So A plus B, which equals B plus A, would simply be A1 plus B1 for the first component, A2 plus B2 for the second component, and A3 plus B3 for the third component. And that is the new resultant vector. By associative, I mean that I could do it in any order. So A plus B plus C. If I have three vectors to add together, I can choose to add A plus B together first. That would be exactly the same as if I added B plus C together first. So that is associativity. So vector addition behaves much like we would expect it to, like regular addition does. Regular addition, when we're thinking numbers, requires an identity element, and the additive identity is 0. So we do have a 0 vector. It's just all zeros in the components, either 2 or 3, or even like 4 or 75 dimensions if that's what I wanted. But a 0 vector has all the zeros. And in addition, we have additive opposites as well. So the vector v plus the opposite of v would have to equal the 0 vector. Essentially the opposite of v, and we can usually just write this as v minus v instead of v plus negative v. The opposite of a vector is simply the opposite of every component of the vector. So if, for example, b is as I've defined it here, then negative b is going to simply be negative b1, negative b2, negative b3. Again, just like we would expect. So that's addition and subtraction with vectors. Multiplication and division are a whole other mess. We don't deal with division at all of vectors. That's just simply not a thing we do. We can deal with multiplication, but there's actually two different kinds of multiplication with vectors. And we'll talk about vector multiplication. It's actually two kinds, actually there's three kinds of multiplication. One kind of multiplication that involves multiplying a scalar by a vector, and that's what we'll talk about today. And then we have two kinds of multiplication that involve multiplying vectors together, and we'll talk about those later. So scalar multiplication, so let's say I have the number k, and I want to multiply it by a vector. So k is a scalar, it's just a magnitude, a numerical quantity that doesn't have a direction. If v is equal to, so let's define v as v1, v2, v3. I've got my three components. And again, if it was just 2 dimensions, then that means I have a 0 for the third dimension. Then kv is going to be each component multiplied by that same value. So k times v1, k times v2, k times v3. Scalar multiplication is also commutative. In other words, I could write this as vector times k. We just usually don't. I'm more likely to write 7v as opposed to v7, just like we do with variables usually. I'm more likely to write 6x than x6. But technically they mean the same thing, and there's no problem with doing that. Scalar multiplication is also distributive over vector addition. So in other words, if I have a scalar times the vector a plus the vector b, that is the same thing as k times vector a plus k times vector b. Scalar multiplication creates vectors that are parallel to the original vector. So if, for example, this is my vector v, then multiplying that by a scalar that is bigger than 1 might turn it into a longer vector, for example, where this could be kv, but it is still going in the same direction. Parallel for vectors could mean they're right on top of each other, because with vectors, we're less concerned about actual position. We're more worried about length and direction. If k is less than 1, so this would be if k is greater than 1. If k is less than 1, then that's going to shorten. Kv, still parallel, it's going in the same direction. And the way I've drawn it, actually, it's specifically that k is between 0 and 1. If k is negative, then I can end up with something going in the exact opposite direction. So let's say, for example, something like this. So this would be kv if k is less than 0. That's still parallel, though. The direction is just now the exact opposite, but it's along the same line. And something that I haven't quite mentioned yet, magnitude. So we have what are called unit vectors. So, I mean, I've mentioned magnitude. Magnitude is a length, but how do we find the length of a vector? Well, in order to figure out what unit vectors are, we need to define magnitude. Magnitude is essentially absolute value. It's what's the numerical length or value of this vector without worrying at all about its direction. So we use absolute value just like we would with numbers, where if I say the absolute value of a real number is just the positive, just how far away is it from 0 without worrying about whether it's above or below 0. With vectors, the magnitude is just what is its length. So if I think about how a vector v has both a horizontal component and a vertical component, so the horizontal component would be, say, v1 in some direction, and the vertical component, v2, some length of that. By the Pythagorean theorem, I can figure out what the overall length of v is. So for example, if I want to know the magnitude of a vector, what did I have it up here? I had it as 4i plus 2j. So this is the magnitude of 4i plus 2j. Well, that's just going to be the square root of 4 squared plus 2 squared, which is the square root of 20, or if I wanted to simplify that, 2 root 5. In 3 dimensions, so for example, I haven't given any specific examples of that, have I? So let's say I want the magnitude of, let's go negative 2i plus 6j plus k. So that's a 3-dimensional vector with a horizontal component of negative 2, a vertical component of 6, and a depth component of 1. The magnitude of that is going to be the square root of negative 2 squared plus 6 squared plus 1 squared. So in other words, the square root of 41 would be the magnitude of that vector. A unit vector, therefore, is going to be a vector in the same direction as each of these vectors. So I'm going to call this one u, but with a magnitude of 1. So in the case of v, this 2-dimensional vector that I started off with, the unit vector for v is going to have to be parallel to v. In other words, it goes in the same direction as v. I put a little hat on it to show that it's a unit vector. But it can only have a magnitude of 1. So in order to make it have a magnitude of 1, I multiply it by the scalar of 1 over 2 root 5. So 1 over 2 root 5 times v. In the case of u, its unit vector would be 1 over root 41 times u. That is then scalar multiplication. It's a vector that is in the same direction, parallel to the original vector, but its magnitude is now just going to be 1.